Thank you very much. Thank you, Anna. Thank you to the organizers for the invitation to talk in this series. I will be, oops. So my talk will be based on these two papers, on the paper I wrote with Paul Marconnet a little less than a year ago, and a more recent one with David Andrio and Tim Vraze from past September. And here's the plan of my talk. Well, in the first part, I will review what we learned from the paper with Paul. And in the second part, I will this will concern 10-dimensional solutions of type 2 supergravity. In the second part, I will take a step back and try to understand these results from a point of view of a general effective field theory. So there's been a lot of effort recently, and not only recently, in trying to obtain realistic cosmologies, starting from the 10 or 11-dimensional supergravities that capture the low energy limit of string theory or M theory. And up until the 2000s, beginning of 2000s, getting acceleration from compactification of these theories was thought to be just as difficult as getting de Sitter space, both of them being excluded by the same no-go, famous no-go, valid under certain conditions that are listed here. In the beginning of 2000s, it was shown that time-dependent compactifications do indeed violate this no-go and allow for accelerated expansion. And indeed, starting with this paper in 2003 by Townsend and Wolfhard, there was a lot of literature where it was shown that transient acceleration from flux compactifications is not only possible, but in fact, it's rather generic. However, until recently, all known examples of transient acceleration were thought to be able to only give you one or two refoldings. So therefore, these were thought to be useless as models of for example, as models of inflation. Now, recently in these papers, Russo and Townsend greatly improved on those no-go theorems, the one that I cited in the previous slide, generalizing it to general time-dependent compactifications. And it was found that de Sitter space is still ruled out by the strong energy condition, at least if the 4D Newton's constant is required to be time-independent in the standard way. Late time acceleration is not ruled out, although no known examples, even today, exist coming from compactifications of 10 or 11-dimensional supergravities. If we require that in the future infinity, the acceleration does not vanish. So you can have late time acceleration that is never vanishing, but tends to zero at infinity. But if you require that it does not, then no known examples exist. So let me start from what we learned in the paper with Marconnet, from what we call the universal compactifications. So this is about 10-dimensional type 2 solutions of we also have type 2b supergravity, but mostly we focused on type 2a. So mostly type 2a supergravity, 10 dimensions of the form a 4-dimensional Friedman, Lemaitre, Robertson, Walker cosmology times a six-dimensional manifold. And that can be either Einstein-Killer, or Calabi-Yau. And we don't care about details of the spaces. For example, if you have a Calabi-Yau compactification, I don't care what the Hodge numbers are, as long as I have a Keller form and a holomorphic free form. And so it was found that these 10-dimensional solutions, this will be important for the second part of my talk, they can be repackaged in a 4-dimensional consistent truncation of two scalars coupled to gravity. And furthermore, these admit a consistent subtruncation to one scalar. Namely, the solutions of this 4D theory lift to 10D solutions.
Dimitrios, sorry, can I ask a quick question here?
Yes.
All the scalars that are outside of the consistent truncation, do they get an effective mass or potential in the running solution, or do they remain as flat moduli? Should we worry about them?
The ones that are outside
the
solution are free parameters of the solution.
So they effectively remain massless even in the time-dependent solution. Okay.
Yeah, at least in the two derivative supergravity approximation in the theory that I'm solving.
All right. Thank you.
So what? Yeah.
So this is you mean at a classical level? It's a consistent truncation at the classical level.
Yeah. So it's
without a symmetry, one loop effects will mix everything up because you need a symmetry to forbid one loop mixing of the operators.
Yeah, so we don't have anything to say about the higher order corrections. This is just two-dimensional, two derivative supergravity solutions. But I will show you some solutions where the string coupling and the volume is large, string coupling is weak, etc. Well, we can talk about this later.
But sorry, to continue on this. So it's not necessary that they stay massless, no? I mean, being a truncation doesn't mean that they remain massless. They could also be stabilized.
Well, it's not. I'm saying there is a consistent truncation. What I'm getting here is 10-dimensional solutions. So it's the same situation as, say, Minkowski 1,3 times Calabi-Yau. You don't care what the moduli of the Calabi-Yau are. You know that it's a solution of the two-dimensional, the two derivative supergravity. So Minkowski 4 times Ricci flat is a solution, at least of the lowest order, at 3 level.
Yes, but that's because the supersymmetry protects it, extended supersymmetry. But when you have cosmology, you have no supersymmetry. Yes. And then you have additional directions, and then it doesn't matter if you're weak coupling. If you generate a one loop mass for them, which is tachyonic, then you need to show that those directions are not any heavier. I mean, like they're not faster decaying than the direction you look at. And without a symmetry, there's no way to forbid a one loop correction making tachyonic or something.
So
like
indeed, you don't have supersymmetry, so you don't know if these are protected. But well, one thing I would like to say about this is that at least for the Calabi-Yau, these are universal truncations. So at least you know that the fields that you're keeping are light. They are part of the universal sector of all the multiplets that you would have in a universal n equals 2, d equals 4 compactification on the Calabi-Yau.
Yeah,
so I'm not keeping any massive.
It's a classical truncation. It's not a consistent truncation. Consistent truncation, you need to have a symmetry. It's a classical truncation.
Consistent truncation, in my terminology, means the solutions of the 4D theory lift to honest-to-God solutions of the 10D supergravity.
Yeah, so consistent truncation, you mean you take some fields and they do not appear in a solution. You can set them to a constant and vary only the other fields. But without the symmetry, so consistent truncation means in equations of motion, there's no mixing between some sector of fields and other sectors of fields. But without a symmetry, loop corrections will always generate operators which mix the two sectors, and so you cannot consistently truncate one sector from the other.
Okay, let me repeat something.
But we can,
I'm solving. So what I said is I have 10-dimensional solutions of 10-dimensional supergravity. If you like to take a point of view of 4-dimensional effective theory or lower dimensional theory, I can also give you this. That's what I'm saying. I mean, what we did in that paper, the one I'm talking about, are 10-dimensional solutions of the form Friedman, Robertson, Walker 4 times 6-dimensional space of 10-dimensional supergravity. So these are honest-to-God solutions of 10-dimensional equations of motion.
Okay, we can discuss it. Okay, thanks. I understand. Yeah, thank you.
And they can be repackaged also from a 4D point of view if you wish to do that. That's all I'm saying. And I'm not discussing about higher order loop corrections for the moment. So let's see. So where were we? Yeah, so they're universal in the sense that they don't depend on the details of the compactification. And yeah, we can have a 4D reformulation if this is wished. Now, with analytical solutions, and this is always possible when you have only one excited kind of flux, type of flux. Although we found also analytic solutions with up to 4 different kinds of excited flux. However, this is not always possible. As long as you turn at least 2 different species of flux, it won't be guaranteed that you have an analytic solution. However, in that case, there's a nice description in terms of a autonomous dynamical system. And this description allows you to have a very nice visual understanding of several different features of the different cosmologies that the solutions of the theory. And in particular, to nicely visualize the condition of accelerated expansion, as I will review. Now, in addition, we found many interesting examples of transient acceleration, where you are in a near de Sitter space, accumulating any number of V foldings that you wish by tuning the solution. Several examples of this, examples of roller coaster cosmology, meaning cosmologies that alternate an infinite number of cycles of accelerated and decelerated expansion, and even examples of eternal acceleration. Now, all these solutions require you to have an open 3D, an open 4D universe, namely a 3D space with hyperbolic 3D space. And at future infinity, they have vanishing acceleration, and therefore no cosmic event horizon. Now, well, in particular, I want to emphasize that the common law that you can never get more than 1 or 2 e-foldings from transient acceleration is false. You can get as many e-foldings as you want. And there's no shortage of examples which exhibit this behavior. Yes.
Yes, sorry, quick question. So am I understanding correctly that in these models, the H goes to 0 at very late times?
H goes to 0 at infinity. At any time less than infinity, any finite time, it is positive.
So for large times, when H is due to these effects, H is very, very small, could it be that corrections change it such that there's just, again, only a finite number of e-folds, or?
Corrections? What kind of corrections?
Well, quantum corrections like the ones Aaron was talking about before, for instance.
Again, I mean, yeah, I don't know.
I'm asking if the results are stable against small perturbations.
Right. So this analysis is has not been performed. So indeed, this is important, as it's been already mentioned, to check if these solutions are stable. We have not done this. So indeed, these are not supersymmetric solutions. And the first question that pops to mind is, are they stable against small perturbations? It's a good question and should be investigated. Right, so here's the setup just to review the notation. This is type 2A supergravity. Phi is a dilaton, F is a 2-form, H is a 3-form, G is a 4-form, M is a Roman's mass. In addition to all the equations of motion coming from this action, the forms of the theory are required to obey these Bianchi identities. Now, this is our ansatz for the 10D metric. We have two warp factors, A and B, one internal 6-dimensional space, which is taken to be time independent. So all time dependence comes from the warp factor. And this parenthesis here is the space with eta the conformal time, and omega is a 3-dimensional space, which can be flat, spherical, or hyperbolic, corresponding to k0, 1, or -1. And for the Einstein frame metric reads like this. So it's a standard FLRW line element, with T being the cosmological time, A being the scale factor, and there are also some other times that are more convenient for in writing the equations of motion. This tau, for example, is another time which is more convenient for the equations of motion. Now, okay, so let me show you an ansatz for the fluxes. And there's a nice thing about this setup is that you can solve all the equations of motion from the outset for all the forms. So here, just as an example to get an idea how this works, here's an example of two ansätze which solve the equations of motion and Bianchi identities for all the forms. The first one is a Calabi-Yau with 3-form and 4-form flux. Omega is a holomorphic 3-form, J is the Keller form, B0, C0 are constants. And the other one, the other example is the Einstein-Keller with 2-form flux excited, and this is a constant here, and the space is negatively curved, and lambda is the scalar curvature, and it's supposed to be negative and it's constant. Now, this solves the equation of motion for the form. We don't have to worry about them anymore. The remaining EOMs are those for the dilaton and the Einstein equations, and they take the following form. So the first one is the internal Einstein equation. They all components reduce to one equation, the first line. The second equation and the constraint are equations, Einstein equations, and this one is the dilaton equation. So as you can see, I can repackage all the equations in terms of the potential, which I called U here, and this U will depend on my ansatz for the forms. So here's what U looks like in different situations, and you can see, for example, the example that you showed you, the Einstein-Keller would be here with CF and lambda non-zero, and K would be the curvature of for the 3D space. And all these equations can be repackaged in a 1D consistent truncation. This will not be so important for this talk. And all these constants come from the fluxes, and we've already seen Cf, B0, C0, and lambda, and similar for the other fluxes. And in many cases, but not all, you can also repackage the equations in a 4D action. That's a consistent truncation by definition. And the cases that are possible to do this are listed here. So in particular, the example that with Einstein, Keller, and the example with the Calabi-Yau is here, first line. Now, as I said, there is a nice description in terms of the dynamical system. That would be a system of 3 first-order equations and a constraint. The 3 variables of the phase space being the velocities, if you will, of the fields A, B, and phi. So the 2 work factors and the dilaton. And solutions would correspond to trajectories in this phase space. And it is possible to compactify the phase space to the interior of a 3-dimensional ball. And important for the second part of my talk, there's always an additional invariant plane in the phase space, which means that we can always have a further subtruncation to a single scalar. Now, as I said, this description allows for a nice understanding of the condition of accelerated expansion in particular. Expansion in this language corresponds to trajectories that are in the upper half of the northern hemisphere. And acceleration means that there is some region in phase space, which here is depicted in green, such that whenever your trajectory passes from that region, that corresponds to a solution that is expanding and accelerating. Well, accelerating and expanding if you're in the northern hemisphere. So the condition of accelerated expansion reduces to the existence condition of an acceleration region. That boils down to what type of flux you have, the existence or non-existence of accelerated region, and it turns out that is easy to achieve. So most cases there will be an acceleration region, and as soon as there is an acceleration region, then there will always be solutions with at least transient acceleration. This is because given a point in your phase space, there will always be a unique trajectory passing from that point. So I can pick any point in this green region and consider the trajectories that pass from this point, and these will have accelerated expansion. So this is why accelerated expansion is generic in flux compactifications, because it's simply easy to achieve a situation where an accelerated region exists. Now, this was already known. We also find some, one could say, unexpected results. So here's an example where you have a fixed point on your dynamical system, which is at the boundary of the accelerating region, which is depicted in green here. And this fixed point is a spiral, stable spiral. This means that trajectories will run into it in spirals, will spiral into it. As they do, take for example this red trajectory, it will start out as a non-accelerating expanding cosmology. It will cross into the green region, start accelerating. It will exit and stop accelerating. Then it will start accelerating again. It will stop accelerating, start accelerating, and so on. And this is an example of what is called a roller coaster cosmology, an infinite cycle accelerating and decelerating expansion. Now, in addition to this type of trajectory, there is a unique trajectory that passes from the origin. Now, near the origin, in the vicinity of t equals 0, you can analytically write out the solution, and it looks like de Sitter space in hyperbolic slicing. Now, see this k equals -1 here, and you can see that in particular at t equals 0, you have a coordinate singularity. The scale factor goes to 0. However, the whole space stays smooth and becomes a Milne universe, which is a regular Milne universe at around t equals 0. The War factor becomes linear. The scale factor, sorry, becomes linear, and you have a regular Milne universe. But the scale factor goes to 0. And therefore, as you tend towards the t equals 0 point, you accumulate an infinite number of e-foldings, simply because your scale factor goes to 0. Yes.
Can I ask a question?
Yes.
So, in this type of examples, typically you have some initial condition with some velocity that force you to climb up the potential, then go down, and that's why I understand that in that region you can have some period of acceleration. But in this case that you have the roller coaster and that continues, how does it look, the potential, or how, yeah, I don't know, is there an intuitive way to picture what's going on? Like, it's not only going up and down, then you go up again. How?
Yes. No, did we have a plot of the potential in this case? I don't think so. Yeah, I'm not sure I can answer this question.
You know, like what forced you to start accelerating again? I don't know, like to.
Yeah, so
once you go down, why you don't continue just going towards infinity and decelerate?
Yeah, I don't think we did this this exercise in this case with the potential, just to see indeed what you say, the oscillation. But yeah, I mean, I think it's an interesting question. Right? Maybe you could just maybe just do this exercise and see more closely what is happening from the point of view of a potential.
But in general, I can picture all the examples as starting going up the potential, right, with some velocity.
Yeah, usually
like the initial condition is typically that, right?
At least for the other example, yeah, this is a standard, in the standard picture that you're talking about, where you go up the potential, at some point you start accelerating as the kinetic energy is dominated by the potential energy, and then you roll down, and then you roll down, and then you stop the acceleration at some point. That's the picture of the transient acceleration. But like you say, I mean, in this case, you would have some sort of oscillation. Yeah, I mean, it's a good question. I don't know how to intuitively understand this. Yeah.
Sorry, can I ask a question?
Yes.
So in your truncations, do you make sure that the size of the compact manifold is smaller than the Hubble scale?
Now, the late time behavior of this is decompactification. So
because if this size of the compact manifold is bigger than the Hubble scale, then you don't really have a 4D cosmology.
Yeah, well, at some point, well, I'll show you an example where the external space decompactifies at the same rate as the 3D space, and I believe in this example the 6D space decompactifies, but at a smaller rate than the 3D space. I'll come to this at the end of the talk.
You seem to be assuming homogeneity and isotropy in your solutions. Do you know which of these solutions is stable when you include perturbations away from homogeneity and isotropy?
No, we have not thought about this at all.
Sorry, one question. Can you hear me?
Yes.
Yes. Is this last call that you saw us somehow generic, or it depends highly on like the initial conditions? Because from the picture that you saw us here, like it looks like the initial point is like the symmetric one over the horizontal axis.
Yeah, the initial point is a fixed point, and the final point. I mean, the trajectories will interpolate between an initial point and a fixed point, so they would all start from here. So this is generic.
No, I mean for the one you have in blue, like the
one.
Oh
no, this is highly non-generic. This is a unique trajectory. The blue one is unique and unstable. I mean, this is unstable in the sense that it's unique. That's for sure. I mean, the other trajectories will be generic.
So it would be like just wouldn't you like just by knowing where the final attractor is and knowing that it has to go through the origin in this like plot, you would say that it's just like a singular trajectory, or maybe different initial conditions could also like lead to it.
This blue trajectory is unique and highly tuned. No, fine-tuned. So there's the unique trajectory that will be unstable. But the other the ones in blue in red are generic trajectories. They interpolate between the two fixed points.
Okay, thanks.
Now, this also shows.
I'm sorry, just one more thing to understand. Something like what Irene was asking. I'm just trying to understand so if you said you can get parametrically large number of e-folds.
Yes.
Human bliss is like where you have a maximum and then you shoot it up so that it almost lands precisely at the top. Is this the right intuition, or?
Look for
Forget
this
about roller
example.
coaster going up and down. Just one. Yeah. How do I get so many e-folds?
Right. So I'll tell you how you get so many e-folds. Then this is independent indeed of the roller coaster behavior. Now take say a generic trajectory like the red one here. I can start fine-tuning it by pushing or at least tune it by pushing this P prime point to come closer and closer to the origin. If I do this, what happens is I make my red trajectory get closer and closer to the unique blue trajectory, which has an infinite number of e-folds. And now, as I do that tuning, this pushing the point towards the origin, I increase the number of e-folds. And in the limit, I would get an infinite number of e-folds. So yeah, so now you're asking in terms of potential, how I understand this. Yeah, I guess I would have to shoot it up higher and higher, something like that. I would imagine.
I think this roller coaster behavior has to do with the fact that there's a curve.
No, but this has nothing to do with the roller coaster behavior. It has to do with the part that is near the origin. That's where you accumulate the. Indeed, this mechanism here is also the same at play in this example, where the fixed point, again at the boundary of the accelerating region, is not a spiral, but a stable node. Now there, the trajectories don't spiral into it, they just run into it. And you have two types of late time behavior. Either you have eternal or semi-eternal. Semi-eternal, by the way, means that it starts as non-accelerating and then accelerates after a certain time forever. So depending on whether it approaches the stable point from the left or from the right, the cosmology that corresponds to the trajectory would be either eternally accelerating or semi-eternally accelerating, or semi-eternally decelerating.
Right.
And it's the same. So this example has appeared before in the math literature. What we showed is, again, there's the same mechanism of transient acceleration with parametric control of e-folds, which operates again a trajectory than the origin that's like this. It's the sitter and hyperbolic slicing. The work factor goes to 0 linearly at t equals 0. And by again forcing the trajectory to go closer and closer to the origin, you accumulate more and more e-foldings from this region. So it's the exact same mechanism. It's entirely dependent on what happens around the origin. Has nothing to do with the roller coaster behavior in this case. But also in the roller coaster, if that's what you wanted to say, you also accumulate an infinite number of e-foldings from the roller coaster region. Every time you cross into the acceleration, you will gain an extra number of e-foldings that is constant, does not go to 0 as t goes to infinity, and remains constant. So every time you go into the acceleration region, you accumulate the same number of e-foldings.
Dimitrios, may I interject?
Yes.
So I think there are two questions here. One is the roller coaster behavior, and one is the semi-eternal acceleration.
Yes.
And the first situation, I think it's really the curvature that makes the difference, because the Friedmann equation is not just about the potential. There's a contributions from the curvature. And so you are not going down the potential. I mean, the intuition that we have for a flat universe does not apply here. Whereas for the semi-eternal acceleration, if we are satisfied with a classical truncation, I think it's also not so difficult to come up with an example with a flat universe where you have accelerating solutions and asymptotically approaching a non-accelerating critical point.
In flat space.
Yeah. So imagine there's a critical point with epsilon exactly equal to 1, which means it's not accelerating, it's the borderline case. You could imagine that you approach from an accelerating solutions all the way. It never reaches the critical point. The critical point is only reached at infinity. And so that kind of behavior can also arise in the flat universe case.
Okay, yeah, I think I know what you're talking about. I'll come to this in a second.
Okay. All right.
Sorry,
but yeah, thank you. Yeah, I think that's a good point.
I'm very confused. May I ask a question?
Yes.
Yeah,
but the fact that the curvature is important in this picture about the potential, I think that's a good point. I think I also reached that conclusion, but I forgot in the meantime that, yeah, the fact that has k equals -1 maybe changes a little bit this picture with the potential that we have intuitively from flat cosmology.
Sorry, just make totally clear. So k-1 is a crucial ingredient.
Yes.
For the total acceleration that you find. Is that correct?
Yes, but that is correct. But I think I know what Gary was talking about. I'll come to this in a moment.
No, but Gary was saying the opposite. He was saying that the asymptotic acceleration in the end does not have to do with k-1. But I understood from your that it does.
Yeah, for me it does have to do with k equals 1, but -1. But I will. I think maybe there's maybe most statements are true in a sense. I'll come to this in a second. So yeah, for this picture to work, you need to have k-1. And a fixed point on the boundary of the acceleration region. Now, okay, let me take a step back now and try to reinterpret all these things from the point of view of an effective theory. And we will be general here. Let's take d dimensions and minimally coupled scalar coupled to gravity and a exponential potential and arbitrary coefficient gamma. We have the two Friedmann equations and the equation of motion for the scalar field, the Hubble parameter, energy, pressure, and the W parameter, and the condition for acceleration boils down to this condition on the W parameter. Now, the phase space description in terms of this theory is given in terms of these variables, x and y, which coincide with two of the variables that I had in the previous part. And the flow parameter of the dynamical system is essentially the number of e-foldings. And you have two equations of motion and a constraint because you have one scalar. Now, previously you had one more. So two first order equations of motion and a constraint. And you see that K0 will put you on the circle, K minus 1 in the interior of the disk, and K plus 1 outside the disk, the unit disk. Now, this dynamical system has the following set of fixed points. You have a set of fixed points for flat space, the P plus minus, that are on the circle and on the horizontal line. And I think I mentioned it before, critical points are in the dynamical system are a special kind of trajectory. Now, they correspond to analytic solutions that are known analytically, and they correspond to scaling cosmology. So the critical points are also exact analytic solutions of the theory, and with scale factor equals t to the power some power. Now, these in particular correspond to t to the 1/3. There is another fixed point for k equals 0. That is the one that has received a lot of attention recently, and that would correspond to scaling cosmology with acceleration. So t to some factor greater than 1, if and only if this condition is satisfied, which is the condition that string theory doesn't like. Or now, in addition to those two that exist for k equals 0, there is also the critical point at the origin that we saw already, and this corresponds to a linear, as we saw already, scale factor. So a Milne universe that in this case happens to be a regular Milne universe. So again, no acceleration for the critical point, so the scaling solution. And another critical point, this P1 here, that in fact turns out to be always on the boundary of the acceleration region, exists for any k. However, if k equals 0, its existence condition is the same as the acceleration condition for the other critical point here, so that string theory doesn't like. Now, perhaps this is the critical point that Gary was talking about, because in this case, you can show that the two critical points coincide. That in the case k equals 0, P1 and P2 coincide, and the condition for existence becomes gamma squared equals to 4 over d minus 2. Now, for k equals 1, the condition of existence is even more stringent, is the same as the strict inequality. So this is just as hard to achieve as achieving this here. And on the other hand, for k minus 1, this condition becomes easy to satisfy in string theory, and indeed we've seen several examples of this. Now, okay, so this I already mentioned. you can also inquire into the stability condition of these fixed points. And now if you're in d greater or equal than 10, this P1, this new fixed point for k equals 1, minus 1s, will be a stable node always. If you're in less than 10 dimensions, it will be a stable node if gamma is less than critical value, that for d equals 4 is 8/3. And if you're above this bound, it will be a spiral. So these are the two scenarios that we saw already. And here is a graphical summary of all that I said. The acceleration region is the green cone here. Expansion is the upper half. Open universe is the inside of the disk, and flat universe is the circle.
Dimitrios,
Now,
sorry,
yes.
To make sure I understand, because I think I had not appreciated this. So then to have this acceleration, these solutions with a hyperbolic external space, you need to have a quite steepy potential. So it's the other way around. It's not only that you are allowed, but you need to have a potential which is quite steep, right?
You need to have a large enough gamma, yes. Larger than...
Yeah, so gamma bigger than this
bigger than this. Which is what you get usually from...
Yeah, it's easier to get.
Now, as I said, the P1 is a Milne universe, not the one at the origin, the one on the yeah. So notice that the P1 is always on the boundary of the acceleration region, while P2, the flat space guy, is of course only on the is always on the circle. And red means it's unstable, and blue means it's stable. So this is also the stability line, which separates stable node from stable spiral. And so as I said, this P1 is a Milne universe, but it's a Milne universe with a deficit angle. So it's of this form, linear scale factor, and A0 is not 1. 1 would be regular Milne universe, but A0 is not 1. This constant is not 1. And also, I should say that solutions are known analytically, not only at the critical point, not only the solutions that are scaling, but also the ones at the asymptote. The critical points are known analytically in the vicinity of the point of the critical point. So, for example, here I give you the analytic form of the solution close to the P1 at late times. So t goes to infinity. It will look so linear scale factor times 1 plus corrections that go to 0 in the t goes to infinity limit. And in particular, the acceleration will be either always positive if this constant is positive, or always negative. So we have two types of approaches: eternal acceleration or eternal deceleration if A1 is negative, which corresponds to the solution approaching from the left or from the right that we saw before. And you can calculate that given this asymptotic expansion, you can calculate the event horizon and see that it's infinite. So these solutions don't have cosmic event horizons. So here's some vector field plot and some nice phase portraits of the solutions. Again, this is semi-eternally accelerating, and this is semi-eternally decelerating, and this is a transient. And also, yeah, so let me show you also this other thing about the parametric control of V-foldings. As you move your curve closer and closer to the origin, you accumulate more and more E-foldings while being in a state where the space is near de Sitter. Here, the light green region is is accelerating region. The dark green region corresponds to W between -1 and minus 0.995. So arbitrarily, I call this dark green region near the sigil. So it's W very close to -1. So you see that the closer you get to the solution near the sitter for more and more e-foldings, and this corresponds to something like 30 e-foldings here. And so to make contact with the first part of my talk, here's the uplift. To 10 dimensions, this uplifts to this 10-dimensional solution of type 2A supergravity, where you have a internal Keller, sorry, this is what? This is Einstein space with negative curvature and constant dilaton. I've also written the 10-dimensional Einstein frame. And here you can see that this decompactifies at the same rate as the internal space. And for the roller coaster example, I also have the same exact mechanism that gives you the control of the number of e-foldings. Here's the uplift to 10 dimensions. This is just some examples to show many different examples are possible. This particular one corresponds to Calabi-Yau with a two-form flux, and the coefficient here is related to the potential from the 4D point of view. And in this example, at late times, the 6D space decompactifies at a rate lower than the 3D space. So yeah, so here's the message of this talk. Maybe we don't need the Sitter space after all, if we can get all the nice things that we need from generic flux compactifications with hyperbolic three-dimensional space at the price of accepting asymptotically vanishing acceleration. And 3D hyperbolic space, we can achieve eternal acceleration, roller coaster, transient acceleration with parametric control of e-foldings. And so this idea is in the air that maybe, in fact, if nature doesn't like cosmic horizons, maybe cosmic horizons are in the swampland. And notice that this if that were the case, that would explain, between quotation marks, not only why we cannot we have a hard time finding the Sitter space, but also why we have a hard time finding scaling solutions with eternal acceleration, namely scaling solutions where the scale factor is e to the power greater than 1. That also would have a finite event horizon, just as the Sitter space. And so I don't know. I think I've run over my time. Maybe I'll just leave you my conclusions to read, and we can discuss them in the discussion session as you wish. You tell me what you prefer.
Yeah, I think it's fine. I mean, unless you want to finish quick saying something, we can stop.
Yeah, well, I mean, just to emphasize that these are solutions, honest to God, 10-dimensional, of type 2A supergravity, no branes or antifolds or anything else. Now, a legitimate question that has been posed already concerns stability. yeah, that has not been studied, and we need to see what this gives. And I also have not discussed moduli stabilization, but my feeling is that it should be possible to we can discuss this to have examples where the moduli are stabilized. At least naively, it doesn't seem to be a big obstacle. Directions, this has not been addressed either, but note that in the solution, at least the examples that I showed you, at late times you have string coupling either constant as a free parameter or therefore tunable, or going to zero asymptotically, and large volume. So presumably they should be under control. And last but not least, yeah, as I said, until recently, people thought flux compactifications can never be used for inflation because whenever you have transient acceleration, you always have one or two e-foldings, never more than that. However, this is not true. So it would be nice to see if we can use these models as models of inflation. And of course, we can cook up by hand some slow roll models of inflation that work really well. But here the point rather is that these models would come from compactification of 10-dimensional supergravities, low energy string theory. So that would be interesting to see if other phenomenological constraints can be obeyed, such as the right power spectrum, etc. So this is under investigation. Hopefully, we'll be able to report on that in the near future. So thank you very much, and I'll stop here.